Okay, so let's start with this photon gas and blackbody radiation. So what are we talking about? We are talking about an electromagnetic field in thermal equilibrium with its container. And blackbody radiation is an example of this, where you make a cavity and let it come to a certain temperature, and then you make a tiny hole and you see, what frequencies are coming out of it. So we have some container, and in this container, the whole thing is isolated, except one little possibility through which you can observe what's really going on. And inside this, you have electromagnetic radiation. This is the problem we are trying to describe. So, and what's really going on here is, again, to give you a bit of a big picture, when we looked at lattice vibration, what is the frequency with which atoms can move about their equilibrium site? That led to the existence of phonons, right? Phonons were how these lattice vibrations are quantized. And quantization of vibrations is something which happens in nature all the time. It's easy to think about quantization if you're thinking quantum mechanics, because it's got the name quanta, but even in classical mechanics, things tend to be quantized, right? So lattice vibration led to phonons. Charge, vibrations, or quantization, whatever you want to call it, led to electrons, right? That's how we describe the electrons. And here we are talking about electromagnetic vibration. An electromagnetic vibration, their quantization is captured through photons, right? So photon captures 1 unit of electromagnetic vibration. The concept of photon was not there until 1905 or 1906, right? That's when Einstein got really bored in his post office job and thought up of all of these things. And so in order to describe this problem, what ensemble should we use? We have 3 options: macrocanonical, canonical, grand canonical. Okay, Nathan thinks grand canonical, I don't know why. Micro, Patrick thinks micro. Is there anyone who thinks canonical? Why?
Because it's kind of like grand canonical, but I don't think photons have chemical potential.
Why not?
Why they don't?
Yeah.
Because they do not really matter.
Yeah, so chemical potential, you're absolutely right. So chemical potential is the cost it takes to create one of something, right? G divide partial G by partial N. Photons are constantly being emitted or being absorbed by the walls of the container. You cannot control the number of photons. It just goes up and down. So I wouldn't go as far as saying that it has 0 chemical potential. What I would say, it's hard to control the number of photons, right? When you set up an ensemble, you think about what is it that you can control. Here, N you cannot control. Number of photons is like in this room, if Kinjal was suddenly splitting into 3 Kinjals and 5 Kinjals and 7 Kinjals, and all of us are recombining, right? It will be hard to control the number of Kinjals. So we don't want to do that. So we'll start with a canonical ensemble. And on top of that, we will not worry about the variable N, because we just cannot control it. So we are going to look at a canonical ensemble, which looks kind of funky. We are going to look at canonical ensemble with control variables V and T, because N is arbitrary. Later, you will see that you could have gotten the same thing if you thought of a grand canonical ensemble with setting the chemical potential equal to 0. You would have recovered the same thing. So canonical ensemble with VT is the same as, this is the same as thinking about Z grand canonical with mu is equal to 0 VT. And but for now, just as you realize that N is arbitrary, and that's how photons are. They are, they just keep popping in and out. So on top of that, now photons, just like all other quantum particles, can occupy energy levels. They can be in a certain ground state. They can be in excited state 1, excited state 2, and and depending on which energy level you are, photons have energy n plus half h cut omega, right? And any number of photons can have the same omega. They are bosons, they are not fermions. Okay, there is no restriction that only 2 photons can stay over here, or 1 photon can stay over here. You can pack them up as many as you want. So any number of photons can have same frequency and pack up in energy level, any energy level. No one is stopping you. So therefore they are bosons. But this brings up the question. We are saying that we have energy levels corresponding to some frequency omega, and depending on which level you are in, you are n plus half multiplied by h cut omega. How about the value of omega? How do we know what is omega for photons? Any idea? Huh?
Yes.
It's related to that. It's related to that. So again, that, go ahead.
Come from like the oscillation of the
Yeah, so you'll have to solve for it. Statistical mechanics is not going to tell you the density of states of photons. You will have a g of omega here also. Remember, for phonons, we had g of omega. And we got to an expression for phonons where we had g of omega in the partition function, right? And then we stopped. We said, now we don't know what g of omega to take. Einstein was lazy, so he said all phonons have the same frequency, right? And Debye said, no, they go as square. So if you solve particle in a box, you can get g of omega. And we will use that expression. And I posted an online PDF which goes and derives g of omega later, but I'm just going to use that. Go ahead.
Yeah, but why were we able to assume it's a harmonic oscillator energy?
That's our model, first of all. And secondly, first of all, it's our model. But on top of that, I think there might be a deeper reason for why the harmonic oscillator works so well.
Is it because the electrons in the material are like harmonic oscillators? Is it related to that?
So,
I don't know.
yeah, sure. So a harmonic oscillator, so again, I'm deviating from StatMech over here, but why does a quantum harmonic oscillator turn out to be a good model for reality? That's the question here, right? So most of the times you are, I don't think I can answer that question here as to why is a quantum harmonic oscillator a good model. Maybe you can answer it on Slack for me. I don't know. I know in classical mechanics, a simple harmonic oscillator is a good model. Why? Because we are staying close to equilibrium, right? And close to equilibrium, everything looks like first derivative is 0, right? And if you're not going too far from equilibrium, third order term, fourth order term vanish. So we can say that, okay, it's just second order term. Why is the quantum equivalent very good? I don't know. I wish I knew. So you can educate me, Patrick, on Slack. Okay, good. It will be useful for a quantum mechanics exam, maybe. Who is teaching quantum mechanics? Okay. So let's start with this. So we can write down the partition function. We will have Q, and Q is going to be going to every microstate and doing e to the power minus beta e nu. Okay, and we know that going to every microstate is the same as going to the frequency for every single photon. So let's say we have photon number 1, and this is where it gets a bit funky. Okay, so we have photon number 1, and photon number 1 can stay in ground state 0, or it can go up to infinity. Photon number 2 can also stay in ground state 0 or go up to infinity. Until how many photons? We don't know, right? So I don't know where to finish this. It can be as many photons as you want, right? We don't know where the summation finishes. It can just keep going on and on. You can think of it as infinitely many photons if you want. Then, given that, you will have energy that goes as, and we know that if the photon is in, we know that the energy goes as n plus half h cut omega, right? Depending on which frequency you are in. So I'm going to write this as n plus half epsilon. Okay, I'm denoting h cut omega by epsilon. Okay, so pay attention what I'm doing here. So now it's going to be n1 plus half h cut. No h cut. I have removed h cut. So n1 plus half epsilon 1. So epsilon is equivalent to frequency, right? It's just off by a scale of the Planck's constant multiplied by e to the power n2 plus half epsilon 2 e to the power.
Missing
Oh.
a beta.
What happened?
Beta. You should have the KBT.
Oh yeah. I forgot beta. Good call, thank you. Epsilon 3, so on and so forth, right? So what I'm going to do now is to collect all these 0-point energy terms and bring them outside. So I will have outside, because this term, if I just look at half epsilon 1 or half epsilon 2, that does not depend on the summation, right? There is no n1 over there, so that, or n2 over there. So that can be brought out. And this will become e to the power minus beta epsilon 1 by 2 minus beta epsilon 2 by 2 dot 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 multiplied by summation over n1, n2, n3, as many as you have. All of them can go from 0 to infinity, e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus dot dot dot.
It should just be one epsilon, right? Why do we have the subscript? It's the same constant everywhere.
No, every photon has its own frequency.
Oh, sorry. Yeah, fine.
Otherwise, it will be game
Yeah,
over.
yeah, yeah. Okay.
Okay, so okay, so here I have assumed that epsilon j is just a notation is equal to h cut omega j. So that's my ln q. That's my q. What do I want next? One moment. I made an assumption in my notes, now it's bothering me. I will ignore the 0-point energy for now. Okay, I'm going to ignore all the terms coming from 0-point energy, and it will become clear in a moment as to why that is an okay assumption. So ignore 0-point energy terms. And the reason it's going to be an okay assumption is because we are normally not interested in Q. In statistical mechanics, how do we get thermodynamics out of the partition function? Arman, huh? And differentiating it once, twice, something like that, right? So if you take a log of this thing, it will be a log of 0-point energy plus log of everything else, right? And when you differentiate that log, much of the interesting thing will just become a constant. That's what will happen. So that's why it does not matter. It will matter. Something will come out, but it will be a constant. So you will see that it's okay to do that. So let's call this equation number 1. Okay, so now I am going to ignore 0-point energy. So if I do that, then Q is summation n1, n2, n3 dot 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 going from 0 to infinity e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus dot dot dot. And again, what the question I think Vedant asked on Zoom is it can get confusing. The reason why we have different epsilon 1 and epsilon 2 is because epsilon is the same as h cut omega. Epsilon j is the same as h cut omega j, the frequency of the jth photon. And we don't know what this frequency is. Later, we will have to introduce density of states like we did for phonons. So this is my Q. I'm going to call it equation number 2. Now, let's look at this one. Can we simplify this? If we had only 2 photons, how would this have looked like? If we had only 2 photons, this would have been summation n1, n2 going from 0 to infinity e to the power minus beta n1 epsilon 1 plus n2 epsilon 2, right? Or summation n1 equal to 0, summation n2 is equal to 0, both of them going to infinity e to the power minus beta n1 epsilon 1 e to the power minus beta epsilon n2 epsilon 2. This means that this first part, e to the power minus beta n1 epsilon 1, can be brought over here, right? It does not depend on n2. So this thing is the same as summation n1 equal to 0, e to the power minus beta n1 epsilon 1 going to infinity multiplied by summation n2 is equal to 0, infinity e to the power minus beta n2 epsilon 2. Is this clear to everyone? It looks funky in summation, but if I had an integral, you would have been very happy about it. If it was an integral, it would be the same as doing, I'm just gonna write on the board. It would be the same as, what's that? Integral dx dy f of xy. And if f of xy is equal to g of x multiplied by h of y, then this integral is the same as d of dx g of x integral dy h of y, right? We do this all the time if the function is fully separable. That's what we are doing over here. So I showed you what it looks like for only two photons. If you had only n1 and n2, if you had infinite number of possible photons, the same idea applies. The summation, instead of writing a summation, you can write down a product over all j values. J is going now from 1 to infinity, right? Fahad, you can take your midterm. So J now goes from 1 to infinity. Why? Because you have photon number 1, photon number 2, photon number 3, so on and so forth. And for each of them, you now have a sum inside, right? Because inside it was a sum. It's a product of sums. And this one goes from nj 0 to infinity. Okay, so this sum is, I think, JP's favorite series, right, JP?
Yeah, but
Why?
isn't how you wrote it in the number 1, isn't that a sum of products? Not a product of sums. I agree that it should be a product of sums.
Yeah, so in number 1, you have to ignore the 0-point energy term. After that, you just need to realize that this is summation e to the power minus beta n1 epsilon 1, e to the power minus beta n2 epsilon 2, e to the power minus beta n3 epsilon 3, and it's a multi-dimensional sum. But each of these can just pop out.
That's the,
Yeah.
That's the individual solutions.
Yeah.
It's just-
It's just a shorthand. So now this sum that you have inside, that's a geometric series, right? We have seen that many, many times. This is, let me write it down on the next page before I cramp too much here. So we have Q. Okay, since at least one person is confused, I will write it carefully. So N1, N2. So the Q is, let's write it down in full. And I know this can be confusing, even I get confused sometimes. So N1 is going from 0 to infinity. N2 is going from 0 to infinity. N3 is going from 0 to infinity, dot, 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 multiplied by e to the power minus beta n1 epsilon 1, e to the power minus beta n2 epsilon 2, e to the power minus beta n3 epsilon 3, dot, 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 right? So what I'm saying is that this one can be brought over here. This has no n2 dependence. This one can be brought over here. It has no n1 or n3 dependence, so on and so forth, right? So this becomes summation n1 is equal to 0 to infinity, e to the power minus beta n1 epsilon 1. Summation n2 is equal to 0 to infinity, e to the power minus beta n2 epsilon 2, so on and so forth. So what is it now? It's a product of sums. And how do we denote a product? We denote it with a pi, right? J is equal to 1 to infinity, summation nj is equal to 0 to infinity, e to the power minus beta nj epsilon j. Okay? Is that clear, Jay? So now this sum, what is this? This is 1 plus e to the power minus beta epsilon j plus e to the power minus 2 beta epsilon j plus dot, 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 right? What is the value of this sum? One over 1 plus? Not 1 plus. Don't break my heart. Yeah, come on. You broke 50% of my heart. 1 minus e to the power minus beta epsilon j. Okay? It's 1 plus x squared plus x cubed. So this thing, Q, is product over j 1 by 1 minus e to the power minus beta epsilon j. That's super interesting. We just got a partition function for harmonic for photons, okay, assuming they are independent harmonic oscillators. We don't know what values should epsilon j take. Remember, h cut omega j denotes epsilon j. So we have not yet talked about the possible values for epsilon j. We know they can be some values. We know they can be some frequencies. We don't know what is the distribution of frequencies. So let's call this as equation number 3. Is this clear to everyone? Good. Now the question is, which is the main question now, is if you have some value of omega 1 and you have energy levels looking like this, and if you have another value of omega 1, or if you have one value of omega and the energy levels look like the one I drew in black, and you have another value of omega and the energy levels look like one in blue, which one has the higher omega?
I have a question, sorry.
Why did my Zoom broadcast stop? Zoom people, can you share my screen? Can you see my screen?
No,
Even now?
no.
The God of statistical mechanics wants you to be in class. What can I say? How about now?
Yeah, I can see it. I can't see it.
This is small omega. This is large omega. At least we are lucky enough that we are in a classroom where EduRoam works, because it's really finicky across campus.
I had a question.
Go ahead.
Could you, because you know they're bosons, could you just start, we're using the canonical approach, but since you know that this is the same as mu equal to 0, can you just start with the average?
Yeah, absolutely.
NG and just multiply?
Yeah, but there is a reason I'm working through this, to show you that you get that same expression. That's exactly what I'm going to show you in 2 minutes, that you get the same expression as we had for Fermi, Dirac, and Bose-Einstein statistics, and put mu is equal to 0. This is why Nathan, who is wise beyond his years, told us to use grand canonical, right? Yeah. But we can blame Aiden for putting us through the canonical route, right, Aiden? Nothing. So the question we want to ask now, you look lost in thoughts. You have any questions?
Sorry, I just got an email to read it real quick.
Okay. So this is small omega, this is large omega, and so the question we want to ask is, for any given omega, what is average value of Nj, which is the average occupation number for any omega j. So if average Nj was 0, how would I fill up these energy levels for a given omega? How would it look like? It cannot be negative. Nj cannot be negative, right? And if the average of certain quantity is 0, what does it mean about that quantity? It's identically 0, right? There is no other way. So if Nj was 0, everything would be packed up in the ground state, right? So I'm giving intuition here that if Nj was 0, it would be all ground state. What do you expect Nj to look like as the temperature increases? It goes up, right? The high value should become higher and higher. Do you expect average Nj to depend on omega? At the same temperature, which one should have higher Nj? The left one or the right one? Right? Sorry, that's confusing. Why should the left one have higher Nj? Jared, what do you think? Spacing is smaller. It's easy to excite. You can get higher occupation. It does not mean that the average energy is higher. because in the right one, even if Nj is equal to 1, it means you are in a higher energy level, just from the perspective of energy. So what we want to do is to calculate average Nj as a function of omega j. And here you will see that the expression we get is the same as Bose-Einstein if you had set mu is equal to 0. Okay, so let's do that. But there is a reason why I'm going through this, because it's a good exercise and it will get you set for future homework problems and things like that. So we want average Nj from Q. How do we do that? What is the definition of Q? If we look at equation number 2, this one over here, which is so equation 2 says that Q is equal to product J is equal to 1 to infinity of, let me write down actually the summation explicitly, it's useful, e power minus beta n1 epsilon.
Isn't it just an N?
Huh?
Product?
What?
Shouldn't the products only ever be to N?
What should be the product? What are you talking about?
The top term of the product
Should be what?
to N,
What n?
big N,
What is big n here?
the number of things.
But photon is not like JP. Photon is like JP, constantly splitting into 2, into 4, into 8. So how do I control that? That's the thing about photons. There is no capital N. I don't know how much they are. I know there is a penalty, and you will see that comes out. You cannot just promote it to very high occupation numbers. There is a penalty. But photons are just getting popped out all the time. That's why we cannot put this. This is important. Pay attention. That is infinite. Okay. Yeah. Good question. This is confusing if you're not paying attention. So now, what we want is to get average Nj from this. How should we do it? We have done things like this a bunch of times in canonical ensemble and grand canonical ensemble. I want you to think without looking up a book online and tell me, how should I proceed? I have to take log of Q and do something to it, right? That's how we get things in StatMech. So it turns out that in this case, average Nj is partial of log of Q with respect to minus beta epsilon j. Let's prove this, okay? So what is log of Q? Log of Q is log of this product. Oh, I should be careful. Sorry, this is not exactly correct. I should write what I wrote back there. Sorry about that. So this was product of summation Nj is equal to 0 to infinity e to the power minus beta Nj epsilon j. Sorry about that. So this is log of product of sum. Nj is equal to 0 to infinity e to the power minus beta Nj epsilon j. Log of a product is going to be sum of log, right? So this is going to be sum j is equal to 1 to infinity log of sum. And I want to differentiate this with respect to minus beta epsilon j. So partial ln q by partial minus beta epsilon j. What would that be? That would be how should I proceed? Should I be differentiating log q or should I be differentiating q and then dividing by 1 over q, multiplying by 1 over q? We're not stuck, we'll get there. Let's proceed from the other direction. We want NJ, right? What is NJ? NJ is going to every microstate, taking the value of NJ in that microstate and multiplying by the probability, right? Everyone agrees with this? So how do we do that? What is the meaning of a microstate? The meaning of a microstate is looking at the value of N1, N2, N3, dot, dot, dot. All possible values of N1, N2, N3, right? And they can go from 0 to infinity. The value of Nj in that microstate. What is P nu? P nu is e to the power minus beta N1 epsilon 1 plus N2 epsilon 2 plus dot, dot, dot divided by Q, right? Okay, now it starts to look better. I should have just proceeded this way. So now you can see that if I keep this summation like this, N1, N2, N3, 0 to infinity, Q can come out of the summation, right? Q has already summed up everything. Q is kind of boring, but all useful. So Q comes out, and then I have Nj e to the power minus beta N1 epsilon 1 plus N2 epsilon 2 dot, dot, dot. Now, is it clear why this partial with respect to minus beta epsilon j might make a role play? So if you think about this thing and we differentiate it, partial of e to the power, let me write it another color. So partial of e to the power minus beta N1 epsilon 1 plus N2 epsilon 2 by partial with respect to minus beta epsilon j. How much is this going to be? What will be the coefficient when we so what will be the first term over here? We are different. Just if epsilon j confuses, think about differentiating it with respect to epsilon 1. If you are doing d of e to the power minus beta N1 epsilon 1 by d of minus beta epsilon 1, what would be the answer? N1 multiplied by e to the power minus beta N1 epsilon 1, right? So here, what will it be? Nj will fall out. And what will you multiply by? The pure exponential, the exact thing that you have, right? That is exactly what we have over here, right? This is exactly what we have over here. So what is this thing? This is 1 over q partial N1, N2, N3 dot, dot, dot from 0 to infinity partial of e to the power minus beta N1 epsilon 1 minus beta N2 epsilon 2 by partial minus beta epsilon j. Okay. This is maybe a lot too many partial derivatives for 11 a.m. Is everyone awake? Okay, Sumin, are you awake? Sure. Okay, good. So let me write down this expression on the next page. So we just showed that average Nj. Okay, let me do the whole thing once again, just to demystify that. It's not complicated. What is average Nj? We go to every microstate, right? Get the value of Nj in that microstate multiplied by P nu. Everyone happy with this, right? That's the definition of an average. What does this mean? This means going to N1, N2, N3 dot, dot, dot from 0 to infinity, Nj multiplied by P nu. What is P nu? P nu is e to the power minus beta N1 epsilon 1 plus N2 epsilon 2 plus dot, dot, dot divided by Q, right? Q does not depend on summation, so we can bring it out. So this is 1 over Q summation n1, n2, n3, dot, 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 0 to infinity, nj e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus dot, dot, dot. And we just showed that this is the same as n1, n2, n3, 0 to infinity, partial of e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus dot, 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 with respect to minus beta epsilon j, right? This is what we showed. Now we can do one more thing and bring the partial derivative outside the summation. Normally at this point, there is one mathematician in the class who really likes real analysis and cringes over the step, but Margot does not like real analysis. So we are, or at least is not that interested in real analysis. So we are safe. No, because we are doing things that are mathematically suspect, but it's okay. Of summation n1, n2, n3, e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus dot, dot, dot. Does this summation have a name? A bit more than that. Come back to StatMech. It's Q. It's Q, right? Just summation of exponential is always Q. So what we have is 1 over Q partial Q by partial minus beta epsilon j is equal to partial ln Q by partial minus beta epsilon j. Okay, so this was the proof. This I will write down over here. Bad idea. Trying to go the other way. It should have gone straight from the definition and then it came out nice. Anyway, so we have this, we have nj. It can be obtained from ln Q by differentiating it with respect to minus beta epsilon j. Let's call this, what equation is this? 3, 4, equation 4. So we don't have the answer yet, but we do have an expression for Q that we calculated by summing up the geometric series, right? And that was equation number 3. Equation 3 said Q is equal to product over J 1 by 1 minus e to the power minus beta epsilon j. So now you can see it's easy to differentiate, right? Q already has this beta epsilon j term that you're interested in. So let's actually do the differentiation. So if we take, but we don't want to differentiate Q, we want to differentiate log of Q, right? So log of Q, the wonderful property of log of product is sum of logs, right? So this is going to be sum over j log of 1 by 1 minus e to the power minus beta epsilon j. Okay, let's call this equation 5. And equation 4 says that in order to get average nj, we have to take this sum and differentiate it with respect to minus beta epsilon j. This sum won't matter, right? Because it's a sum over different epsilon j values and differentiating only with respect to one of them. So everything else disappears. I'll write down equation 5 once again. So we have ln Q is equal to sum over j of ln. So we can, instead of writing ln of 1 over something, we can write a ln of that thing, me e to the power minus beta epsilon j. So, and nj is partial ln Q by partial minus beta epsilon j. So what's that going to be? That's going to be partial with respect to minus beta epsilon j, and we can totally get rid of the summation because the other j's don't matter. Whatever j you have, that's the only thing that matters. Of ln of 1 minus e to the power minus beta epsilon j. This is just one line of algebra. It's log of x, so 1 over x, and then one more derivative. So this comes out to be partial nj is equal to, so log of x, the derivative of log of x is 1 over x. So this is 1 minus e to the power minus beta epsilon j. And then you have x. So simply e to the power minus beta epsilon j. Or if we divide by this thing in the denominator, this becomes 1 over e to the power beta epsilon j minus 1. Or average nj is equal to e to the power beta epsilon j minus 1 to the power minus 1. And if you remind yourself of the expression we derived for Fermi Dirac and Bose-Einstein, that looked like e to the power beta epsilon j minus mu plus minus 1 to the power minus 1. So this equation, which is equation number 6, if you compare with equation number 7, we showed this last class. What conclusion can you draw? This is Nj for photons. So what can we conclude? Photons are bosons with mu equal to 0. They don't have a chemical potential. Okay, go ahead.
So the term we know first when we calculate G, we ask epsilon beta.
It will give you a term. You're correct. So what you're Abhindev, right? I somehow keep calling it Abhinav because it's a more common. Anyway, so what Abhindev is saying that why did you ignore this one? He's angry for that because if you differentiate, you take log of this, what will you get? Minus beta epsilon 1 minus beta epsilon 2. If you differentiate with respect to beta, what will you get? But they are constants. That's the point here. They don't depend on anything. So you don't get 0. If you differentiate it second time, then you will get a 0. In the first time, you do get a certain number. But the reason we don't care about it is because that itself does not have any temperature dependence. So, but good point. Yeah. So that's what we get. Photons are, this is also a popular qualifying exam question. Why? What does it mean when I say that photons are bosons with chemical potential 0? Same thing for phonons. Phonons are bosons with chemical potential 0. Okay. Electrons, however, they have chemical potential. You cannot just create an electron out of nowhere. Photons are bizarre.
But these are ideal gases, right? that we're going with?
Whatever we derived is using ideal gas, but photons turned out to be like that even in reality. They just come and go in and out.
What
And
was,
go ahead.
so I get the point that we're using the whole canonical approach to show specifically that mu equal to 0.
Mhm.
It seems like a circular argument because you essentially use the fact that they're photons to make all those 0 to infinity sums in the first place. I mean, that they're bosons, not photons.
Yeah.
And then you do all this to get that expression. So you can directly just start with the
I really want-
But
I
what's
really wanted to start directly. Yeah, I agree.
intuitive argument for mu equal to, assume I didn't have a canonical approach at all.
Yes,
where
I have directly written this, and that's the smart way to do it. But there is a reason I did this is because together we worked through this derivation. That was
no. I don't have an objection to that. I'm just asking what's the, like, assume the canonical approach didn't exist. I knew this average expression was there. What would, prompt me to say that mu would be 0 for photons?
I would have said that from the very beginning. As soon as I said that photons are being emitted out of the wall and being absorbed out of the wall with no cost, that is the same as saying mu is equal to 0, right? So when you're doing a chemistry reaction, what's the origin of mu? It's the driving force for matter, right? In order to drive matter from one place to another place, there is cost that you have to pay or to create matter, right? And this thing. So here I'm not proving that mu is equal to 0. Mu is equal to 0 falls from the direct fact that we already assumed in the very beginning that photons are created or emitted with no cost. So that already had that. So this is not a proof that mu is equal to 0 for photons. That absolutely, you are absolutely correct. We assumed in the very beginning. Okay, good. Now, quantum mechanics gets really funky. This is not a quantum mechanics class, and I'm not going to get into that. how do photons get created, what's really going on. You're taking your quantum mechanics course, go and ask your professor over there. I mean, quantum mechanics, the more you think you understand it, the funkier it gets. But we are going to focus on this one. And in this case, this expression that we derived, so which we wrote, e to the power beta epsilon j minus 1 to the power minus 1. And what was the connection between epsilon j and omega? H cut omega, right? Or h bar omega. So what we are showing is that if you have a certain frequency omega, that n is going to be e to the power beta h cut omega minus 1 to the power minus 1. The first person to derive this was Max Planck. This is known as the Planck distribution. So this is giving us a sense. You remember the plot, the figures that I drew, that you have lower frequency, the things are separated by a narrow gap, and you have a higher frequency and things are separated by a higher gap. It is telling you exactly what is going to be the average occupancy given the value of omega. So this is a powerful approximation, okay? Powerful equation. Again, derived for ideal gas, but turns out to be bizarrely true. Turns out to fit the background radiation in the universe to 10th decimal place. So don't be an ideal gas hater. It's really, really powerful. When on Tuesday, we will go beyond ideal gas, right? So the reason we had ideal gas so far is because we were looking at non-interacting systems. That's how we end up with ideal gas. What's the simplest gas you can think of, which is non-ideal? Van der Waals gas, right? So next class, we will see how the Van der Waals actually comes out naturally by thinking about interactions in the system. So in your PChem, you have all looked at Van der Waals gas, right? And Van der Waals gas, you introduce ad hoc corrections, right? You say this is the size of the gas, and you introduce another term which accounts for pressure. Starting Tuesday, you will see how these terms actually come from a first principles, from looking at the interaction between two molecules, which is like that part a lot. So this is Planck's distribution.
Does this system have no free energy?
He's asking really philosophical questions. It's a canonical ensemble. I can always write a Helmholtz free energy.
But
it won't be expensive. There is no n.
No, I mean, I can also, with the grand canonical approach, if mu is 0, then the Gibbs free energy is 0, right?
Mm-hmm.
And for it would be minus kBT ln Q for the free energy here. But what does that mean? Like physically, why am I, like if I don't, I'm considering this chemical energy potential thing, but then, sorry, chemical potential thing, but what does it mean? Oh no.
Okay. I would like someone to answer it on Slack and have a discussion on it, okay? And there are many of you who don't use Slack. Your participation points will be deducted. Where is Kiet? Yep. He comes and tells me, Suemin just told me there is a method on Slack, and he's telling me this on Slack. I'm like, this is kind of ironical. You're on Slack right now. Please use it, okay? So Kiet, this is a question for you. Kiet will answer or attempt to answer, okay? Enjoy. And if you don't enjoy it, you know who to blame. You know, right? Vedant. Now, this is a very good point. I want to have a discussion. Okay. The reason I'm not getting into that is because I want to finish the expression for Black-body radiation. Otherwise, it will tangle from next Tuesday and we will be in trouble. Let me finish this and certain things let's have on Slack. So we have the average occupation number for a given frequency, which is powerful. Now we get to the main problem which we started with, which is if you have this container in which electromagnetic radiation is in equilibrium with the walls of the container, and you can study the frequency of the radiation that is coming out, right? And you can study so if you can study the frequency of the radiation that is coming out of this container, the problem that we really wanted to solve now, or Max Planck wanted to solve 125 years ago, is average energy per volume at frequency omega. That's what Max Planck wanted to calculate. And the other thing he wanted to calculate is average energy per volume at any frequency. Okay. So the first thing he wants to do is to calculate small u of omega. How do I calculate this from the expressions that I have derived so far? Is anyone brave enough to help me with this? It's per volume, so I should divide by volume. I helped. Someone else has helped. Kinjal, what do you think? What else should I add here? We have all the ingredients, except one, which I mentioned we will be using. So at a given frequency, what is the energy? The energy corresponds to the occupation level, right? If you are in occupation level n, the energy is n plus half h cut omega. So on an average, what is going to be the energy? Average n plus half multiplied by h cut omega, right? So this is going to be average n plus half multiplied by h cut omega. Is that it, or are we missing something? Density of states. We don't know what is the probability of observing that frequency. If the probability of observing that frequency is 0, then there is no point, right? Imagine, and this is really goes back to the Einstein model, right? Einstein said g of omega only one frequency. So you could calculate this value for any frequency. But if that frequency cannot happen, then there is no energy, right? You won't see it. So this has to be multiplied by g of omega. Okay, this is my u of omega. Clear, Kinjal? Okay, good. So, and again, I'm going to ignore the 0 point energy. Yeah, go ahead, Patrick.
Can you explain the last part
Which was the last part?
where you replace the quantum number n with the average?
Because I'm talking about average energy. That's why average is coming from here. I'm not talking about energy in one quantum state. I'm talking about what you will measure in a classical experiment. That's why. Again, I'm going to ignore the 0 point energy. It does not matter for thermodynamics, which kind of also makes sense, right? 0 point energy is a purely quantum phenomenon. So if your 0 point energy starts to matter in your classical expressions, then something very funky is going on, right? So I have u of omega is 1 over v g of omega average n multiplied by h cut omega, ignoring 0 point energy. And for average n, I can use Planck's distribution. What is that? So u of omega is equal to 1 over v g of omega 1 by e to the power beta h cut omega minus 1. And in the numerator, we also have an h cut omega. So that's my average. I still don't know the g of omega. So I'm not completely done yet. Now I have to think about g of omega. So for g of omega, this is something, if you're taking quantum mechanics, if you're taking quantum mechanics, you can solve for it, or in the notes that I posted. So just like for phonons, I just gave you a value of g of omega. I did not try to derive what it is. That's what I'm going to do here, right? This is beyond StatMech. What is the frequencies that can be taken is a question your StatMech cannot answer for us. So g of omega for a particle in a box, you can show, turns out to be v omega square by pi square c cube. This is ridiculously similar to Debye's expression. With the only difference, this is true for all omega. There is no cutoff. Why did Debye have a cutoff in the frequency? Aurelia, you remember? When we were thinking about lattice vibrations, we said, okay, so what does high frequency means? High frequency means, low frequency means you're moving like this, right? High frequency. And frequency is 1 over wavelength. And Debye said that you have a classical material, the smallest wavelength you can have is this distance between two atoms, right? So if you have a biological system, you cannot really have things closer than, let's say, the distance of a hydrogen bond, right? So if the distance has a smaller cutoff, the frequency has a larger cutoff, right? So we mentioned this in the notes. For photons, we don't have to make any such arguments. So it can happen for any frequency. So for photons, what was the value of integral g of omega for phonons? 3n, right? We had 3n oscillators. For this, it diverges. For photons, it diverges. There is no meaning of integral g of omega. It's going to diverge. So this is g of omega that I can use. And let's call this, what's my equation number 10, and this is equation number 11. And again, I posted notes which does g of omega in great detail online. You can read that. So this tells us that equation 10 plus 11 gives us u of omega is equal to h cut omega cube by pi square c cube e to the power beta h cut omega minus 1. Planck was the first person to derive this also, and this is Planck's formula for black body spectra. Equation 12. The final thing that I want to do today, so this is the average energy per volume at a given frequency, where we have taken into account the density of states of that frequency. Okay, and that you can call it cheating because I don't have time to derive that here. You know, it will take half a class to do that, but I posted the notes for that. So we get this expression. Apart from that g of omega, we have not done any cheating, right? Everything has been done in a truly first principles manner, so which is kind of amazing. Now we can calculate capital U, which is the per volume, which is integral 0 to infinity. You go to all frequencies and multiply and sum it over. Okay, u of omega for all frequencies. So this is the average energy per volume coming out of the black body. This integral is h cut pi square c cube 0 to infinity d omega omega cube by e to the power beta h cut omega minus 1. If you substitute x as beta h cut omega, this integral becomes h cut by pi square c cube 1 over beta h cut to the power 4 0 to infinity dx x cube by e to the power x minus 1. Has anyone seen this integral before or remember the value of this integral?
Zeta function.
Huh?
Zeta function?
That's a good guess. You're a smart guy. You're wise beyond your years.
134.
Okay. No one, it shows up a lot. It's got a bizarre value. This integral is pi to the power 4 by 15. So what have we just shown? We have just shown that capital U by V is pi square, is h cut by pi square c cube 1 by beta h cut to the power 4 pi to the power 4 by 15. It's approximately true, but to a high precision. Okay, let's go one step further. Let's remove beta and let's bring back kb. So beta is equal to 1 over kbt. So what is going to be the temperature dependence of U? T to the power 4, right? In the denominator, you have 1 over T. So this gives us U by V is equal to pi square kb to the power 4 by 15 h cut cube c cube t to the power 4. And this is the famous Stefan Boltzmann law. So, okay, now I want to go to this expression that we derived, the Planck's formula for black body spectra. And let's try to sketch it. So equation 12 is U of omega is equal to h cut omega cube by pi square c cube e to the power beta h cut omega minus 1. So if you are observing, if you have an instrument which can tell you what energy do you have at a given frequency, okay? So let's say you have a curve that corresponds to this. First of all, how would such a curve look like? How would it behave at high omega?
exponential's gonna.
Exponential is going to dominate, right? That's always a good guess. Anytime you see an exponential and there is something about it, oh, exponential dominates, it beats everything. So at high omega, it's going to look like e to the power minus omega. At small omega, what's going to happen? It goes to 0, and you have to use L'Hospital's rule, and it will go to 0 as omega square. So at small omega, it will go as omega square. So let's say you have such a curve that you have obtained, and you have and you have Max Planck's formula for black body spectra. And you want to fit Max Planck's formula to this curve. What parameter can you manipulate in order to fit to this curve? What is the only parameter here that you can really fit? H bar is given.
Well, you didn't know each other.
Oh no, H bar C. Okay, I will give you the answer. Pi, H bar C are known. So what is left? Beta, the temperature. So this is what goes back to the cosmic background explorer experiment. People found that instrument allowed them to measure this curve. They went and fit beta, and they got the temperature around 2.7 Kelvin. This was the first real measurement of the universe's temperature at the early universe. And so the PDF I posted, the guy clearly, I don't know who, I think it's the guy who wrote it, clearly gets quite emotional about this. He's like, this is light that has traveled for like, I don't know, 13 billion light years, right? It has been traveling and traveling and traveling, and it fits to this curve with an 10th order decimal precision. And it gives you the temperature of early universe to 2.7 Kelvin. And then I think people were able to derive the temperature of the early universe using other ideas also. I don't know what they are, but this number of 2.7 Kelvin persists. Why is the early universe 2.7 Kelvin? That I don't know. What happened, that's because that's where you have complication between quantum mechanics and gravity, right? You have to reconcile all those things. But to me, it's quite amazing because I don't think I understand quantum mechanics very well. I definitely don't understand gravity. I understand StatMag. And with a bit of StatMag, the only cheating we had to do was to take G of omega. And we get this expression, which is like incredible. So that's why I like this a lot. Why did we do all this? So next class, we are going to move to interacting systems. Why did we do phonons, electrons, photons? Just to show you that the power of StatMag, these three ensembles, if you're willing to assume something as simple as ideal gas, allows you to cover such diverse things, right? So in your research, you will be faced with a DNA, an RNA, some battery materials, some fancy semiconductor. All you need to do is to think about energy levels, write down the partition function and get going. And you can obtain all sorts of things and make assumptions. It's okay, because here we made, this is crazy, right? This is ideal gas assumption, and it's giving us things like this. The early universe was clearly heavily packed. It was not ideal gas, right? And yet it is giving us things like that, which is absolutely fascinating. So next class, we will start with interacting systems, with Chandler has a whole chapter on it. And yeah, so see you next class.